Okay, welcome you all in my presentation. So thank you, Lucas, for introducing. Um, Today's presentation is going to be a hands-on tutorial on, as Lucas said, a new NILM toolkit. So it's not actually totally new. It's a complementary toolkit to the toolkits that are out there and have been used for years. The hands-on session is directly related to our recent paper, so I kindly invite you to check it for further details. It's called Evoking the Full Potential of Neural NILM on Automation, Hyperparameters, and Modular Pipelines. And yeah, the work that I will be presenting is a result of a project that I co-authored with and I worked on with several scientists in NILM scholarship, actually they have more experience than I am, but maybe during this project our focus was more on how to improve the efficiency and reproducibility. So I will not jump up directly to the notebook and the coding because I think that providing an overview of the toolkit first so that maybe developers or people who are interested in further improving or introducing more toolkits will be introduced to how the toolkit was designed, and they will have the opportunity to contribute if they would like. So I will start with the motivation for our project, and I would like to quote a sentence from a paper that was published about comparability in NILM. So the authors mention a very interesting sentence in their abstract. So they highlight that despite all the progress and the tremendous work and enhancement that have been made in NILM in the recent years, the performance evaluation and comparability are still open research questions. So we don't have standard evaluation setups or a consensus on how to perform evaluation. And this is actually negatively impacting the reproducibility, comparability, and also the efficiency of researchers. And I believe this was the starting point for our work. So in summary, we have, as I said, an exploding number of models that is recently proposed, which doesn't have to be a bad thing. Actually, it's really nice to have a lot of development and to notice that NILM is gaining interest from scholars. But the problem is that we have sometimes the details of the methodologies that are missing in some publications. Sometimes the code is not shared, or if it's shared, it's not compatible or it's not working. Sometimes we have a gap between the code and the results, and all these issues together are negatively impacting reproducibility and comparison. So then if we look at the NILM scholarship, so this is basically a co-occurrence network that was generated from the papers that were published in the last 5 years. We will notice that 99.99% of the models are all machine learning models. And if we look at the machine learning field, I believe that comparability and evaluation are a bit more advanced. So the idea was to see how we could borrow some of their best practices and adopt them in the NILM scholarship to help improve this aspect. And to the best of our luck, we found a lot of actually papers on the topic that are suggesting best practices catalogs and a lot of checklists that can be used to ensure that the work will be reproducible and replicable. But the main idea was to see what are the tools that could be used by scientists to improve their efficiency when coding and when performing experiments, and to help them save a bit of time. And as I said, that was the focus. Then we found that many of these best practices are very relevant to the NILM research. And then we started by analyzing the toolkits that are in NILM. So we have plenty of them, and I believe that NILM TK is the most popular one. It has a lot of advantages like data parsers, it has advanced functions for exploratory data analysis, and the recent API actually is very helpful. So it helps to decouple the model and to implement deep baselines. But still, it falls short in 4 aspects. So we have first the problem that the NILM pipeline is generally the same. It's either a sequence to sequence or a sequence to point, but still, if you go to the toolkit, you will have to implement everything from scratch each time you want to test a new model. The second problem is that we don't have pre-designed experiments that are available. So sometimes you will fall short in and waste a lot of time in identifying what's the best sampling rate, what's for each appliance, what's the best window length, what's the starting time, what's the ending time, while in the literature you will find a lot of work that already did this. And then we have also the lack of best practices. So we don't have any feature that allow to perform advanced evaluations and like hyperparameters optimization, for example, for the window length at the input. And the third is the poor compatibility with deep learning frameworks. So for now, the toolkit, the NILM-TK, will impose to use TensorFlow and Keras, which is actually a bit exclusive for some scholars who are working with other frameworks like PyTorch. And this creates actually a bit of problem for comparing between different models, even when the code is available. Okay, so this, I presented here the main toolkits that are available. So we have NILM-TK contrib, which is basically directly linked to NILM-TK, and it's only compatible with Keras and TensorFlow. And then there is another toolkit that was recently proposed, I believe in April or May, that's called Torch NILM, and it's solely dedicated for PyTorch models. It offers some advanced features like hyperparameters and cross-validation, but still these features, I guess, could be only used with baselines. So if you will introduce a new model, I would say your own model, you will not be able to use them, which is actually a bit problematic. And then came our work called Deep NILM-TK, and the idea was to develop something that would gather the community under the same umbrella. So it doesn't matter which deep learning framework that you are using, you will be able to use the toolkit. So we integrated Keras and TensorFlow, also PyTorch, and these advanced features. And we added something like experiment tracking and results logging with the possibility of testing a new model and integrating it directly. I will present shortly how the toolkit was designed. So in summary, Deep NILM-TK is an open source package that was designed specifically for deep models. It implements a very generic and flexible NILM pipeline that is totally independent, as I said, from the deep learning backend. For now, it considers only PyTorch and TensorFlow, but we took into consideration that maybe in the future there will be other frameworks, other deep learning frameworks that will be developed, and this we have created an interface specific for that. The training and the testing are fully compatible with NILM-TK, and it integrates several MLOps tools. So this is actually the big picture of the toolkit, and each block in represented in the pipeline actually is replaceable. So it's like a piece of puzzle where you can remove each block and replace it with a custom one, but still the pipeline will run, and this will save you a lot of time. So it starts with the pre-processing, the feature generation. Then we have the data loader and the model definition that needs to be defined. For the data loaders, so generally it's a sliding window that is used for implementing NILM pipelines. But what's implemented here with PyTorch is that the slide-in window is not generated as a whole, because it would consume a lot of memory. It's generated batch by batch, which actually is a great advantage. And then we could, for the training, there is 3 options. You could use cross-validation, hyperparameter optimization, or just standard training. So train, test, and train, validation, and test. And as you could see here in the top, we provide an interface for different deep learning backends. So for now we have TensorFlow and PyTorch, but this one could be extended only by using this interface. And then we have the inference and the post-processing, which can also be customized. Okay, so these are the main 3 features that are extra implemented. I will not take a lot of time explaining them, so that I save a bit of time for the code. So we have time split cross-validation that is directly adopted from Keras, which is dedicated specifically for time series. For hyperparameter optimization, the toolkit uses Optuna, and for experiment tracking, the toolkit uses MLflow. Okay, and then we had the idea to address this problem of templating and to use data templates that have already been designed. So we don't have to waste a lot of time checking what's the best sampling rate and what are the best buildings to use, what are the best start and end time for testing and for evaluation. So this could be predefined and shared by scholars who have deeply investigated this thing for others to use it. Okay, so it's here. And actually the main advantage of this is that it allows direct comparison and saves resources. So if there are many papers who are proposing models who have been evaluated on the same template, you will not have to redo all the experiments. And it allows also fast prototyping, since we have already published in our paper a benchmark for some templates and some appliances. So if you want to test, you will not have to rerun all the baselines. You will just have to run your model and perform direct comparison. Third, it allows to build standard evaluation snapshot data sets for NILM. So this is the first step, I would say, to provide, to standardize this evaluation process. And at the end, as I said, it allows to join forces. So there are people who are working solely on the energy data and others who are more proficient in model development. And it could be a chance to join forces and so that each party could benefit from the work of the other. Okay, that was everything for developers. So for the overview of the toolkit, I don't know if we could continue directly to the code, or we should maybe take a 10-minute break, or maybe have questions, or.
I would say that we can continue, but I don't know if we have questions. The audience, please use the chat option if you have questions. Otherwise, we will move forward. Because we had a long break. We've been having quite a few breaks this afternoon.
Okay.
I don't see any.
I guess I go forward. No questions?
No questions, so please go ahead. And thank you.
Okay, just. Okay, before I go to the notebook, I would like to show you our repository. So this is the repository of the toolkit. It's available on GitHub, and you have.
We are still seeing the PowerPoint. I don't know if you.
Okay, okay.
Yeah.
Here. Now, yeah. You see my browser.
It's okay.
Okay, so this is the repository of the toolkit. You have available documentation with tutorials if you are if you would like to use it, and also if you would like to extend. So everything is here with proper documentation. And yeah, for installing the toolkit, actually you have two options. The first one is to use a Conda environment, so you could install it using pip on your laptop. Or if you are not a big fan of environments and you face dependency problems, we also provide a template project based on Docker that you could directly fork and use to define your project. So this is actually straightforward. This is the best option, but still some people would like to work with local environments. Also, if you're looking for NILM datasets to test with the toolkit, we provide the most famous datasets in a repository on Drive. Yeah, I guess that was everything on the GitHub. So let's jump directly to the code. I just here first described a bit the toolkit, but I guess it's not necessary because I have already done that. For the packages, so to run the notebook, we will need NILM-tk and deep NILM-tk installed. And here, okay, and here they are both installed from GitHub. For NILM-tk, I'm using a version that I forked recently, actually a while ago, because the official one is for somehow not accepting to be installed for some reason. Yeah, I will run this because it takes a bit of time. Also, to use the notebook, you will have, I forgot to mention this, you will have to create a copy in your account and link it to a repository where the data is available. So for the data set that we will be using in this session, it's going to be UKDAL. I will leave it running. And for the hands-on session, we will see three parts. So we will start by seeing experimenting with the baselines. So we'll see what are the main models that exist. We will see how you can benchmark your own models in just a few lines. And then we will see one of the MLOps features that is available, which is hyperparameter optimization. Okay, it's still running. For today's session, I will be using PyTorch solely, but you are invited if you want to test with the TensorFlow. I just have to warn you that it's a bit naive trainer. It's only compatible with sequence-to-point model. So I will start with the first part, which is experimenting with the baselines. The toolkit implements the main baselines that are already available in NILM-tk contrib. So the idea is to extend what is there and to complete it, as I said before, plus three other models. So the first one is very similar to sequence-to-point with an attention mechanism in the middle between the encoder and the decoder. The second one is a bidirectional, is a transformer actually with a bidirectional attention. And the third one is the UNet model. I guess it's a popular one. It uses a convolutional network for upsampling and downsampling. So for to run an experiment, you will have to define several parameters. I will just show the code. So all these parameters are here. So they are very similar to which I tried to keep the same names and to make the names very easy to understand or straightforward. And since I know that most of you are not familiar or don't have a lot of time to read about each parameter and what are the possible values, I tried to provide here, so this is a good feature for Colab, the possible values that could be used for each parameters. So for the model type, for the sequence type, and so on. And for the data template concept that I previously talked about, as I said, we have suggested 4 templates in our paper. But for simplicity purposes, during the current notebook, I created a custom one just for NILM 22. And yeah, so that it contains very few amount of data, and it will not take us a long time while training and testing with the toolkit. So the other, okay, here important parameters is a data path. You will have to specify the correct one, otherwise it will not work from your drive, of course. The experiment is just a label, and the results path is actually important because this defines where everything will be logged and where all your results will be saved. So it's important actually to save it. And here, if you specify a folder, it will be directly saved into your drive. So no need to worry about. Okay, for the next cell, we will start running experiments. So we will use sequence to point for data generation. We will not use the RNN, it takes a lot of time. We use sequence to point baseline, and as I said, considering the appliance, the fridge as an appliance, and a very short sequence length of 99, and for a maximum only for a single epoch, I would say, please. Okay, 1, okay. Yeah, so to run an experiment, all you have to do is to import the experiment template, and then you have to provide the data path and the name of the template. So here it was NILM 22, the list of your appliances, and then the list of baselines backend. So here basically you could run another baseline if you want with TensorFlow backend, and it will work. It's supposed to work directly. And this actually allows to test different contributions that have been developed by different people, but still under the same NILM pipeline. And then 2 parameters that also are important is the input sequence length and the output sequence length. And why we differentiated between these parameters, because some models work with sequence to subsequence paradigm. So it's a bit tricky there, and we offer this for more flexibility. And yeah, once you have defined here, so there is the set of appliances, you have your model, and the data is defined in the data template. All you have to do is to provide the label to name your experiment and where all the data will be saved. And this last parameter is also actually important because it will log all the parameters that have been used in the execution environment, and it will allow you to perform a lot of comparisons. So I will, this will be seen in the last part of the tutorial. Yeah, so if you would run it, I think I already have run this, so probably it will directly load the model and generate the predictions. Okay, I'm sorry, I have to execute this one. Apologize, I have to connect to my drive. Yeah, I forgot here to mention that you will probably face some dependency problem, but it's okay. These are all related to some other packages that are specific to Colab and not to the toolkits. Okay, now it's working. So if you run here, the model will not retrain, probably because yeah, okay. So here it's directly generating the results and it's loading from a checkpoint because I already run the cell to save a bit of time. So I will show you here. This is where the results will be saved in your drive. So I specified here the sequence to point as path. And if you go to the sequence to point, you will see that this is for the baselines. And if you go to the checkpoints, you will see that it's organized by appliance. And for each appliance, you will have the different models. And for each model, you will have different versions. So sometimes you test with the same model, but with different model with the same name, but different parameters. Maybe you would like to change the version, you would like to change the data. That's also possible. All you have to do is to specify a different version number, and this will get you, will allow you to run the same and structure your output repository in a very organized manner. Okay, and also the results from the disaggregation will be saved directly here. Okay, it's still running. So I explained here a bit of what each repository contains. The checkpoints, as I said, it's the checkpoint where you can load your model. Okay, so it's finished. Yeah, so here it's totally compatible, as you can see, with NILM TK contrib. It's very similar, but the idea was to complete it. So here we have somehow of a good F1 score, but a bit of bad mean average error, but still it's good for only one epoch. And then the second part would be about if you want to test your own model. Actually, here it's a bit tricky. There is a lot of options in the toolkit. So if you want to implement a standard sequence to sequence or sequence to point models using the mean square error loss, you already have some abstract classes that you could use, and you will only have to extend them. Because the pipeline is the same, you will have only to redefine the architecture of your network. But if you want to use more complicated loss functions or prediction generation, you will have to define a PyTorch model or a TensorFlow model with two extra functions. So the first one is the step function that will allow you to define how each batch is treated or processed during training with a loss function. For example, the BERT for NILM uses a specific loss function that relies also on the state generation. Or for example, if there are models who are using the pinball loss, which is becoming a bit popular. And the second one is the predict function, which helps to define how the predictions are generated during inference time. So for the code that I will use here, I will keep it simple and use a sequence to point model. That the aim is not to go very complicated, but to show you how you can simply use the toolkit. So this is the abstract class I was talking about. Since we're going to be using simplest a standard sequence to point model. All you have to do, as I said, is to define the network architecture and then the forward function, which is specific for people who are used to develop in PyTorch. These are the basic two functions that we use. Okay, for this function, I will leave in the part of hyperparameter optimization. And then if you want to run the experiment, it's always the same manner. You will have to use a template, and you will have to define a NILM experiment, and you could pass your model class as a parameter, and then the pipeline will run. So basically, this is, if we consider that this is the standard sequence to point model, everything will be the same. Only this part will be changed. So it's the architecture of the model that will change. And all you had to do is to write only the class of your model and then run the experiment directly. I will not run this because it takes time. Okay. Okay, and then when you, I will explain this further. If you want to have an experiment, you want to use a benchmarking study, perform a benchmarking study, you can do so. So again, you will have to define your baselines. And then to add your model, you just have to add the study or the NILM experiment and extend the template. And this will run directly. So as I said, I will not run it. It takes a bit of time. I already ran this, and so it's saved in the benchmarking folder here. And you could check here the checkpoint. So if you go to the fridge, you will have two checkpoints. So the first one is for the sequence to point, and the second one is for the model that we have created. Okay, then if we look here at the results again, so we have approximately the same results considering the mean average error, but really poor results considering the F1 score. So the idea is if you want to see what's the problem, it's also straightforward. You can download, you can load actually the pickle file where the results are saved, and you could directly have the results in a nice plots and in one data frame. So here we could see that this new model didn't really learn how to predict the values of the power consumption of the fridge, which is not the case of sequence to point baseline. And here it's more clear in the picture. So we have sequence to point that already have learned something in one epoch, but the other one is still didn't get it from the first epoch, I would say. The last part is hyperparameter optimization. And again, I will not run it. I guess we are running out of time. You could just use it by defining a NILM experiment and using these two parameters. So everything is the same. You will have just to specify that you want to use Optuna, and you will have to specify the number of trials. These are two important parameters. And then you will have to define this function in your model, which is suggest hyperparameters that basically tells the toolkit how to generate automatically the parameters that are changing from one execution into another one. So for example, here it's the window length that is changing for the input size. And if it's not open, it will add 1. If it is, it will leave it as it is. Okay, this was presented. And then it's always the same. So we will have to define the baseline. Here we have no baselines. You will have to run your study, and the results will be saved in whatever you specify. And here, the main idea is that if you go here and you will check, you will see your checkpoints, you will find that you have, so this is for the first version that we executed, you have different folders for each checkpoint and for each model that you can directly use. And of course, yeah, it's always performing very poor for the F1 score, but still, it's only the best model that have been selected during the training that was tested. So this is the main advantage. You will not have to do any manual intervention. Everything is performed automatically. And the last main advantage I would like to say of the toolkit is the experiment tracking. So if you will go to your results, the results folder, and I guess I shared the link here, you will see an ML folder called ML Flow, and if you go inside, it has a folder called ML Run. So if you download this, it takes a bit of time. So I already did download it. But I will not present what it is in it. So could you still see my screen?
Yes, we were seeing the screen.
Okay.
Now we can't. No, you can again.
So, okay, I'm sharing my terminal now. All you have to do is, as I said, to download that folder, and then you supposedly will have MLflow installed. So if you will run MLflow UI, you will have a very nice user-friendly interface in your browser. I will stop again sharing. I will show my browser again. Okay, so this is the interface. And here I'm presenting from other experiments that I did, because the one that we just did in Colab is very simple and it will not allow to compare. So this is basically a login interface of all your experiments. And you will have here the experiments that are organized per appliance. So here I have different appliances that I have been testing recently and with different models. So for each appliance, I can check what are these models. I can perform comparison directly here, and I will have the parameters that have changed between one model and the other that are highlighted directly here in the interface. I could also study how the losses have changed. So for example, I could use the validation loss, I could use the training loss, and you could even perform some zooming. So here it's not the same because some of them have been cut by the early stopping technique. So this is not really helpful. Maybe we could do it like this or not. So yeah, here you could see that there is how the validation loss was changing. And you could see here which model and which validation loss have been locked. And yeah, all this is practically at no cost. You didn't have to code all of this or to write notebooks to analyze the data or something. And also there is something here interesting that allow you to study how everything, how the run was changed. So here, for example, we could see the model name and, for example, the input sequence size. And then we want to compare between the different models. And this is also possible. So we will have to see what are the main parameters that have changed, and then how did this impact all your metrics. So this actually is a very straightforward package that help you to save a lot of time. Okay, so this being said, I wouldn't say that the toolkit that we are proposing here is 100% perfect. It still has a lot of limitations, I would say. So first, not all the models for TensorFlow have been integrated. So there is only the sequence to point, which is actually a bit of a huge shortcoming. And Deep NILM TK in its current version focuses only on event-less deep learning. So we don't have a pipeline for event-based models, which are actually gaining a bit of interest recently if you take a careful look at the literature. There's also something very interesting that I had the chance to work on recently. So considering the toolkit in its current version and every other toolkit, there is only centralized training option. And we don't have any option for decentralized training. So basically using federated learning on the edge device, which would make more sense in the case of smart grid. And I guess it would be interesting to integrate all this in future work. I guess that was everything from my part. I would be very happy to hear from the audience if they have any suggestions or maybe some things that they saw about the toolkit that pleased them, or they would like to develop more or join us. So everyone is welcomed on board. And again, I would like to thank the committee program for having me during this presentation. Thank you.